This screencast, we're going to be going over the answers to the solutions and net ionic equations homework. So question number 1 was just a bunch of net ionic equations, just so we had practice. Hopefully you sat down with your reactions to know page and tried to follow all of those rules. A lot of the reactions are double replacement, but we have learned a few synthesis reactions, and we'll be learning some more decomposition and, of course, single replacement. 1A is a acid-base reaction, and one of your products is always going to be water. Water is a molecule, so don't try and split it into ions. KF, which is formed, is soluble. Anything bonded to something in group 1 always is. We don't show HF as ions because it is a weak acid, and so it is splitting up and getting back together, so we can't represent something as ions when it actually isn't. And KOH is soluble because, again, you have something in group 1, then canceling out your spectator ions, you end up with this net ionic equation. 1B, we have magnesium sulfide and some nitric acid. You have to make a decision about your nitric acid. It is a strong acid, so it will split into its ions. This is a double replacement reaction. Magnesium nitrate, all nitrates are always soluble, so this does split up into its ions. HS does not split up because it is a gas, and it's one of those gas-forming reactions that you have to recognize. We did not split up magnesium sulfide because in the problem it says it's a solid, so it will react, but at the beginning, because this is what we're showing, the reactants, what's there at the beginning of the reaction and what's there at the end of the reaction, we cannot show magnesium sulfide as ions because it's a solid right now. It will dissolve in the nitric acid and will react, but at the beginning it is a solid. C, we have acetic acid poured into sodium bicarbonate. So these are this is the acid-base reaction that you would do, or at least, anyway, the reaction that you would do in a volcano, like in the 3rd grade. So you have your acetic acid. It is a weak acid, so of course you don't split that up. Sodium bicarbonate or sodium hydrogen carbonate is another name for that. It is a solid because in the problem it says powdered, so we're not going to split that up. It's going to form sodium acetate. All acetates are soluble, especially if it's bonded to something in group 1, so we have our ions there. And it does form carbonic acid, which immediately breaks down into water and carbon dioxide. Again, these are your gas-forming reactions that you just need to know and be able to recognize immediately. In 1D, we have ammonium hydrogen sulfite and perchloric acid. So, and both of these are solutions. This will split up. Most things bonded to ammonium are soluble. And perchloric acid is a strong acid, so it also splits up into its ions. We form ammonium perchlorate, and we form sulfurous acid, which breaks down immediately into water and SO2. Again, a gas-forming reaction you have to be able to recognize. E is one of our reactions to know. We've got solid lithium and it's added to water. These guys are part of the alkali metals, and that's because they form basic solutions when mixed with water. We are going to form a base and hydrogen gas. Water is a molecule, so again, we do not split that up, and lithium is solid. Notice there is no charge because lithium is a metal and it is metallically bonded to other lithium atoms, resulting in no charge. Over here, though, when lithium becomes an ion and bonds to hydroxide, you do have to show it as a ion charge, and this does split up because it's group 1. Similar situation here, we've got potassium oxide added to water. Reactions with water are some that we are trying to memorize, so it's in our reactions to know part. And we have our potassium oxide added to water. This is going to result in just a base, no hydrogen gas like the previous problem. Granular potassium oxide means it is a solid. Water is a molecule, so we don't split either of those up or represent them as ions in our net ionic equation. Potassium hydroxide is soluble, so we are going to split that into its ions, making sure you balance as you go. Here we have a nonmetal oxide added to water, and it is going to form an acid. And the acid here is sulfuric acid. That is a strong acid, so it does split up into its ions. We don't split up our two molecules. In H, it's solid magnesium oxide and exposed to carbon dioxide, and that is going to form magnesium carbonate. Besides the fact that most carbonates are insoluble, the other reason we don't have this shown as ions is because there is no water involved here, so we're not dissolving anything. Magnesium carbonate would just form and would be in the solid form, resulting in no ionic charges. I is a single replacement reaction. It's one that you have seen. Copper put into silver nitrate. Of course, nitrates are all soluble, so they do split up, and that's one of the few compounds that will combine with silver and not form a precipitate. Copper comes in and replaces the silver, so we start to see silver precipitate, and we're going to form copper nitrate solution, which, if you remember, solutions that involve copper are blue. And they could ask you about some of those practical aspects on the AP exam about those chemical reactions. So the resulting net ionic equation looks like this. Remember, a solid piece of copper is metallically bonded to other atoms of copper, and so there is no charge here and cannot be canceled out with copper here, which is an ion form because it is separated from the nitrate by water. Similar situation goes on here with the silver ions versus the precipitated silver crystals that would be forming as a product. Make sure that you do balance for charge, and that's really what's going on here with these coefficients. And then the last one, at least as far as our net ionic equations go, we've got solutions of hydroxide and nitrate. Both of those are soluble. It is going to form strontium nitrate, which is soluble because all nitrates are, and iron 3 hydroxide, which is a precipitate. Most hydroxides are insoluble. So when you get rid of your spectator ions, this is what you end with. But when you write net ionic equations, you want your coefficients to be the lowest possible whole number ratio. So just reduce that down to get your final answer here. Okay, question 2 on the homework, and ask about the intermolecular forces. So intermolecular forces affecting atoms from weakest to strongest. So we would have started with London dispersion forces, and that's also called an instantaneous dipole, because when we say that the electrons are being shared equally, it's not equal all the time. And because it's not equal all the time, when other nonpolar molecules get around more nonpolar molecules, that there is an instantaneous attraction there, but it doesn't last very long and it's not very strong. It does increase with size of the molecules because you end up with more electrons and they become a little more polarizable. Then you would have dipole-dipole intermolecular force, forces of attraction. Those occur between polar molecules, and it's that partial positive attracted to that partial negative. It is stronger than London dispersion forces, and also becomes stronger the more polar the bonds are, which would result in a more polarizable atom or molecule. So then we have an extreme form of dipole-dipole, and that is hydrogen bonding. It exclusively involves hydrogen, and it has to be a hydrogen directly bonded to F, O, or N. That makes that hydrogen very electron deficient, makes it hungry for more electrons, and that allows it to become attracted to an unshared pair on a neighboring molecule. And that unshared pair is generally on fluorine, oxygen, or nitrogen as well. Okay, so in order to lead us through this, we're number 3, I had you go through the substances. Since we're still practicing our Lewis structures and bonding, I made you go through this progression here so that you could figure out what type of molecules you have. And we're going to pause right here.